go back to this. So a regression task, for example, right, in 1D, I mean, let's just go back to that same example, right, which we actually mentioned, right. So just as you have a movie, let's say, right, and then you want to be able to say, right, you want to be able to give sort of, right, a rating to that movie. Rating could be, we have so many organizations, right, that do a rating. I mean, I don't know, right, I have some names here. Some like IMDb, I think that's the internet movie sort of a database, and then you have some Rotten Tomatoes and all that. I mean, I don't know, I'm not an expert in all that, but yeah, right. I mean, you can take examples like that, and what you have is the input, right. Like I said, could be who is the actor, right, who is the director. Maybe, right, who is the something else, who is the guy who composed the music, whatever, right. I mean, you can put all of that, right, and then what you want is a block, right, I mean, which takes as an input, and this by itself could be an MLP, right. It has several layers, and at the output, right, I mean, you want right, you want to ask, for example, right, I mean, in terms of the IMDb rating, what would this mean for a certain rating, IMDb, and then what would it mean with respect to another agency, how would it rate it, and so on. Now, in all of this, right, you need something to be able to train, and for example, right, this could be any number between, let's say, 0 and 10 or something. Right? Somebody just rates it as 4.5, somebody gives 4.6, somebody says 9.8, somebody gives 9.95. Right? Any number you can give. It does not have to be a probability or anything. Right? It's simply a rating. So somebody rates the movie. Now, what you can do is, you can actually in all of this, right, in order, for example, tomorrow, if some movie, right, you get access to. And you know the actor, director, and all of that. So if you were to put that as an input, if this MLP had been trained, right, then what you could do is you could just take the new information that you have, and then ask, right, what would be the IMDb rating and all, and maybe if these people actually rate it, right, you expect that what your network tells, hopefully will come close to what, let's say, these agencies will eventually rate it. But for training, you need all that information, right? So you need to be able to go back, dig up, movies for which ratings are already available, and for each one you look at who was the actor, who was the director, who was the music composer, who was the producer, whatever, it doesn't matter, right? So all that you put in, and then you say what was the IMDb rating, what was the Rotten RT, what was it rating, and then what was some other, right? I mean, a critic rating maybe. So you can have all those rating values, and then what do you do? So for example, if you think of this as your Y, then over examples and examples, right? I mean, you cannot train a network with just one example, right? I mean, you have to give several movies for which you should have this information available, right? I mean, so that is where this training thing comes in, right? You have to train the network. That means you have to tell this network that, hey, look, right, we have this information with us already, that if these are the people, if this is the kind of thing that you get, then the output rating rate turns out to be this, and similarly for the other movie and so on, right? So what you really want is a prediction of these values, right? Y, that means each of these ratings, which could be a value, let's say anything like between 0 and 5 or 0 and 10 or whatever it is, and you want the cost to be such that, let's say, right, if I have L examples, right, of these, okay, that means I have L movies, and let's say Y, okay, what is the dimension? Let's say Y is some, let's say, right, m dimensional, let's say critics and whatever, right, it's some m dimensional output. Then what you really want is this number, right, or this kind of a value, right, the scalar value, which is like y hat of, let's say, I comma j minus y of I comma j squared, right, and summed over, let's say, I goes from 1 to L, and then j goes from, let's say, 1 to m, right, and you have got, let's say, right, 1 by L or 1 by L into m or whatever, right. I mean, you can actually scale it, right, whichever way you want. Now, what you want is for every I comma j, right, you want this number to be as small as possible, so that a prediction, right, happens well, and if you can train a network such that, right, so something like this is called a loss function, right. So the loss function, whenever we say loss, right, typically we want the loss to be a small quantity, right. Nobody likes a loss to be big, right. So therefore what we will do is we will say that, right, this needs to be minimized, right. Minimized with respect to what? Right, minimize means what? Minimize with respect to something, right, and what is that something? That is something will have to be the weights and the biases sitting in the MLP, right. You want to what do you say, right, you want to be able to arrive at these weights and these biases such that, right, at the end of the day, this cost, right, which you are looking at, tends to be as small as possible. And then, okay, if you try to do that, then let's hope that, right, you have finished training and you are actually happy, okay, with how you have trained. It doesn't always mean that you have done a good job just because this error has come down. There are issues like overfitting and all that, but let's kind of stay away from that for the time being. Let's just assume that, right, you have done the training, and then the idea is that, right, once this is over, then then give me a new movie for which you have some information. I will put that in, and then instead of you telling me, I will have this network tell me what kind of a rating, right, it might have. Okay, that is kind of a regression problem. Again, typically for images and all, there are so many of them, right, which come under right, such a task. The other thing is actually, so right, this comes under a regression problem. The other one, right, would be what's called a classification problem. Classification, where you could have a distribution, right, which you're trying to match. So it's like saying that, right, I'm trying to build a network such that, let us say that I have a true sort of a distribution, which is, let's just take a right simple case, a true sort of a distribution, which looks like, let me say that, right, that my y is some 0.3 for some class, for some label, 0.2 for some other label, and then 0.5 for some other label. Let's say that these are probably, right, and what do you call, so this is an urn with some balls, let's say, right. So I've got red balls with this probability, let's say blue balls with this probability, y with this probability. Right. Now what I want is a network, right, which can actually take examples, right, of the kind that I have, and be able to actually get to a y hat, okay, or q or whatever, right. Okay, you want to call this y hat, okay, y hat, right, such that y hat should be actually as close as possible to y. That means I'm learning this one, a distribution, right. So I want to know, like, right, how many of those red balls are there, how many of those white balls are there, whatever, right, blue balls, yellow balls, and so on. And let us say that, right, again, right, now all of this loss function is very, very important. Okay, it's not always true that, right, every time you can have just a loss function like this and walk away. Okay, I'm just giving the simplest of all, right, which is like an MSE or something. Okay, for the earlier example, a regression. But then sometimes, right, depending upon what kind of a network you have, you have other losses of the kind. Sometimes they are called adversarial losses, and so on, right. So it doesn't always mean that, so this will typically be one component of your losses. There could be others. Okay, you can have a sum of different losses, and then you have to weight them. Okay, because you cannot equally weight them then. If you have multiple losses coming in, which is also possible, but then what you'll have to do is you'll have to carefully weight each one of them, and then those are called hyperparameters, because, right, you don't learn them typically, right, you don't learn them typically, you just play around and find out, right, which one of those parameters work best for your task. Now in this case, right, let's say that I have a network, right, which gives me an output, right, while I am training, right, I get a value, like I just have an example here, so 0.35, so let's say 0.65, right, this is what I get. Now I want to compare it, how well have I done, right? This particular this one, a network that I have, which seems to have done a prediction of y, and it has given me a y hat. Now I have some numbers there, right, which of course sum up to 1, as they should. Now I could then ask, right, no, is it okay to do the same thing which I did earlier, right? Can I just do some y minus y hat, right? For every element wise, can I take the squared error and sum them up, right? You could do that, right? Nobody stops you, but then the thing is, right, because of the fact that there is a difference between that and this, because this being a probability sort of distribution, right? You want to do something which is more aligned with that, right? So you want to kind of make use of the fact that there is kind of information content and so on, right? And how you do that is as follows. Okay, now let us say that, right, for an event A with a probability, let's say P of A, for an event A with probability A with probability P of A. Okay. If you want to kind of look at what kind of information content, right, it has, then the information content, right, you can write the information content. Suppose you indicate this as information content as, let's say, what do I have, I of A, right? Okay, so the information content in A, right, this you can typically give as minus log of P of A. Right. What this actually means is that, if it's a certain event, right, then there is no information. Like for example, if let's say P of A is 1, it's a certain event, right, then in that case, there is no information, that's the right known that you can get out of that. If A is a very rare event, right, in which case P of A is a very small number, right, then you sort of think that the information is probably very high. It's like saying once in a while, right, a tsunami comes. Right, probability is very low, but then the fact is that that's like high information, right, and therefore this information content and this minus, right, as you know, right, is there so as to take care of the fact that P of A is between 0 and 1, right, therefore you want the information content to be high, right, for values less than 1. Now what can happen is, right, so if you have, let's say, multiple events, right, now if there are n events, okay, so if you want to look at the expected information, right, if there are n events, let's call them A1, A2 all the way up to, let's say, AN, with, let's say, probabilities, let's say P1, P2 all the way up to Pn, then the, right, expected information content, or what is called the, right, expected values, you all know, the expected information content will then be what, according to you? What would you write the expected information content? That means the right expected value of I of A, right, over all the events will be summation Pi. Yeah. So I mean, in simple terms, I of AI, right, I going from 1 to n, which is summation, which is minus summation Pi, and then log Pi, right. I mean, P of AI is Pi, okay. So log Pi. So I going from 1 to n, right, and this term, right, is called actually entropy, right. For those of you who come from information theory background, all right, I mean, you know that, right, this term is called the, right, entropy. And what you are trying to do, right, in a sense is, right, I mean, so Pi is actually a true probability, right, and if you actually right, if you think of a term like this, where you have got minus summation Pi log Qi, right, where you're trying to approximate, or in that example, right, we had like yi and yi hat, right, similar to that, right. If you had Qi and you're kind of, right, trying to push Qi as close as possible to Pi, because Pi is actually the, right, true this one probability, and you want Q to look as close as possible to P, then this one, right, again, of course, I going from 1 to n. See, for example, right, if you had, let's say, if you had just two classes, then right, I mean, then in that case you will have like, P into, let's say, I mean, if you had let's say, right, P1 as P, then your P2 would then be, say, 1 minus P, and similarly, right, Q1 would be Q, and then, right, Q2 would be like 1 minus Q, right. But then typically you will have like n number of classes, and such a thing is called actually a cross entropy. This is called a cross entropy. And you can show that this cross entropy, right, is always, so let me write this, so cross entropy is always greater than or equal to this entropy. The proof for this is fairly involved, okay, but a shortcut, right, which if you are willing to accept something, then a shortcut is this. There is something called a KL divergence, okay, KL divergence. Okay, we will see this at a much later time, but this is called Kullback-Leibler divergence, okay, Kullback-Leibler divergence. And what this just like right, I mean, you try to analyze, right, through a mean square error, right, try to find out whether, let's say, two functions are similar or not. Similarly, this gives you a notion of a distance between two distributions, okay, distance between two distributions. So I mean, if this number is smaller, it means that, right, they are really close, distance between two distributions. So, for example, in this case, I can write Kullback-Leibler between P and Q, and the way, okay, this is just a symbol, okay, with a two, what do you call, two lines, okay, in the middle, okay, and this is typically, well, right, when you can have something like summation P of x log P of x by Q of x, and this log can be anything, okay, to the base, okay, it's up to you, whatever you want to choose. Typically, it will be a natural log, and okay, which then means that, right, this is like P of x. Okay, summation, of course, log P of x minus, okay, and this also, right, the summation Pi log 1 by Q. You can write it in whatever form you want. So here it's like minus Px log Q of x, right, and this KL is always right, is a quantity such that, right, it's again a number, by the way, right. So it tells you how close the two are, and this is actually, if you accept this, that the scale divergence is always going to say, right, greater than or equal to 0, then right, clearly Px log Px is actually greater than or equal to Px log Qx, right, and therefore if you take the minus, right, on either side, right, then you have minus Px, okay, of course, on a summation and all is there, okay, Px log Px then be less than or equal to minus summation Px log Qx, okay, and this is your, say, entropy, and this is your This is a cross entropy, right? So this cross entropy is always a number greater than or equal to the entropy, okay? And the idea is that when you try to right, minimize, okay, so for example the loss there was something like a mean square error when you had a regression task, right? So here typically in a classification problem you will try to minimize the cross entropy loss, okay. That's why the loss functions and all, right, will change, okay, when you go from one task to another. I mean, right, if you have a regression task, then the cost is typically a different kind, then minimize the cross entropy loss, okay. So in a classification problem, right, this is what you would have, and as you can see, right, the first term really has no effect. I mean, this is because pfx log pfx, right, that is really a true probability, right. So a network does not really, right, it does not matter, okay, what that number is, because it's already a given number, whereas what really q depends upon, so the second term, right, is what really matters, right. In this, if you look at it, it's the second term that matters, because your network has to actually do a prediction of q, right. So therefore the second term is actually cross entropy, and right, that is the one which you want it to be as low as possible, because the lowest, right, which you can take is the value like, pfx log pfx, right, at which time your KL divergence becomes 0. That means your q and p are almost identical now, right, identical in the right Kullback-Leibler sense, okay, in that sense, okay. And therefore, right, if you see, people keep on talking about this cross entropy loss, right, and that is when they talk about a classification problem. Right now, let's say that I have these loss functions, right, whatever, it could be a regression problem, it could be a classification problem, right.